Mhm. Can you please confirm if I'm audible? Oh, yeah, thank you. Maybe we can start in a minute or so. Okay, so I think we can start now. So welcome to the live session for week 6 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting in solving some of the week 6 assignment problems that have been given to you in your NPTEL assignments. So we are already at the half part of the course. We have already covered some of the very basics of different devices. We started with the introduction, that is the silicon-based and electronic devices, and then we went towards more conceptual basis on the density of states and all those things, that how actually the transport happens in a actual semiconductor. And then we studied about like the very basic of the devices, that is a PN junction and the BJT. So we covered like a very minor part of the BJT, because considering it is not as much important as we have the diodes and field effect transistors. So if we have a good understanding of diodes, I mean, that will eventually help us in making the band diagrams and all the learning all the concepts of let's say all the field effect transistors, etc. So as you can see in this particular week, what do we have? We have the starting topic as the field effect transistor, which is, I would say, the most important topic for this course, as well as even if you're going for research or any industry oriented job. So this is the main device that eventually comes into the picture. It is you can say it is some kind of enhanced version of the bipolar junction transistors, or uh, a combination of several diodes containing in a single device. So it is again categorized into some old devices or some new devices such as junction FETs, MES HEMTs, etc. But most of the things that we will be covering will be related to the most important device, that is a MOS device, which is a metal oxide semiconductor field effect transistor. So we have two things here. One is a MOS capacitor, in which we'll be seeing some of the CV characteristics. So this particular topic can maybe go up to 2 weeks. Maybe in the next lecture also we'll try to wrap this up, and then we will eventually go towards some of the modeling that is being given in your week from week 7. So there is drift diffusion models that has been given, and then hydrodynamic and all those different type of transport models that are been given in the course. So I'm assuming that we already have a good understanding of the of making the band diagrams currently, and we know even if we, let's say, we take a different polarity of the different type of devices, we can make the band diagrams of it. So, I mean, with that, we can move ahead and we can start with the topic of field effect transistor for this particular topic. Sorry, for this particular lecture. So I'm hoping that you have already covered the videos that have been uploaded by Professor Vivek Dixit for this particular week, and so let's see what is an actual field effect transistor, or what are the basic advantages that we have over the, let's say, the existing device, that is a BJT and diode. So as the name suggests, as in the name itself, it is written that this is a field effect transistor. So field effect transistor means that it is somehow affected by field. So we already know that now the field is what field we are talking about is electric field. So whatever we'll be applying in, let's say, as an input or an output, it will be inducing some of the electric field in the device, and that is somehow converting the device into a, let's say, a switch or an amplifier. So hence the name field effect transistor. Now, some of the basic properties of these field effect transistor is, first of all, these are majority carrier devices. That means if you remember that in let's say in a BJT we have both majority and minority carriers, which are helping in having the current flow, etc. So these devices are basically majority carriers. That is, these are unipolar devices. That means the overall current conduction depends only upon either electrons or holes. It is not like a BJT in which both of the electron and holes are responsible for the complete passing on of the current. So unipolar means either electron will be participating in the conduction or either holes will be participating. So it will be dependent upon what type of device we are talking about. Then what else do we have? This is a voltage control device. So if you remember, the BJT that we studied was the current control device. That is, it is getting controlled. The overall transport was getting controlled by the injection of the base current. But in this, what we do is we apply a voltage which is at a contact which we call as gate. So I'll let you know what is gate, etc. But this is a voltage control device. So by applying certain voltage, we are able to control the current in the device. Then, I mean, if I say in a long haul, so one thing is the fabrication of these devices is easier as compared to, let's say, a BJT. Why that is? Because in general, what it has is it's only take one-fifth area of, let's say, a BJT. So this is the most important consideration that we see whenever we are talking about, let's say, industrial applications or no, or let's say the actual practical applications. So we want less and lesser area in any of the device. So these devices only contributes to one-fifth of the area as compared to a BJT. So this is a very general number. It is not true. It is not always true. But yeah, this is a very generic number that only 20% of the area has been taken by these kinds of devices as compared to the bipolar junction transistors. So these are some of the perks that we have. BJT itself has some of its perks, like it offers a better transconductance, etc. But considering all these perks, most of the state of the devices that we see, even the FinFET, I mean, you might have heard these names like FinFETs, nanosheet, which comes into the category of gate all-around transistors. So these are all basically depends upon the principle of these field effect transistors only. So all these are unipolar. That means either electrons or holes are uh, contributing to the overall conduction of the current, and this is how, I mean, we'll be going forward. So as I have already said, this is a voltage control device, and yeah, so is there any doubt in this particular slide that I need to say again? Okay, not so. The basic classification of FET that we have, so as you have seen in the course outline, so we have like different types of FETs. So the some old kinds of FETs are called as junction FETs, which is what I'm writing as J FET. So let me write junction also. And then the second FETs that I have already given you the idea that these are the most important FETs are the MOSFETs. They are again subdivided into two categories. One will be the enhancement type, and second will be the depletion type. So since we are actually be going through the working of actual MOSFETs, how it actually works, so we'll be mostly dealing with the enhancement type. So enhancement type, let me not go through very deep into the what is enhancement depletion, but in very layman language, we can say that enhancement MOSFETs turns on only if you apply a certain amount of voltage, and it turns either and otherwise it always remains off. So depletion MOSFETs can remain on even without applying the voltage. So we are not very much bothered about these things. So the actual working that we'll be seeing in this particular lecture will be MOSFETs, and that too for the enhancement type. So we'll start not even with a MOSFET. So we'll start with a even a very basic device than MOSFET. That is what you might have heard from the lecture. It is a MOS cap. So MOS cap is nothing but a MOS capacitor. So the, as the name says, capacitor is nothing but a device that can store charge. But don't get away by the name. Capacitor is like a passive device which stores charge, but MOSFET can give us actually is an active device which can either act as a active device in saturation or in linear or in, let's say, as a switch or an amplifier. So we'll be watching out the working of it. So let me give you a very brief schematic of it. So MOSFET is nothing but we have a certain metal in which we will apply. So this is a contact in which we basically apply certain voltage. So this input is what we call as gate. Then we have a oxide layer which is this shaded portion. Then we have some kind of semiconductor present here, which is what we call a substrate. And at the bottom, we again have this contact, which is what we call as the substrate contact or the body contact, which is in general zero. So we'll be not talking about the body modulation as of now. I'll just denote this contact body with, let's say, B, and this gate with G for this whole lecture. So don't get confused by the analogy. So we have two contacts, as I've said. One is the gate contact, which is the this one. This is the metal contact. This is the body contact, which is again the metal one. Oxide is in general what we use is SiO2 because of the very nature of it, because it is very easily it can easily be grown on the semiconductor substrate, and substrate is again silicon only. So if I try to say, as the name suggests, it is a capacitor. So let me try to ask you a certain questions. So we know that capacitor is nothing but, let's say, it is having a metal on one side and other metal on other side, and in between we have some dielectric, which is, let's say, some epsilon, and the difference between these two metal strips are D. And in this capacitor, what do? We apply a certain voltage. So let's say this particular capacitor has a value C. So can anyone tell what is this capacitance? What is the basic formula of this capacitance? Anyone? So it repeat again. So let's say, as I said, I have a capacitor which is having parallel plates, metal plates, having a constant dielectric in between with a distance d. So what is this capacitance? I'm assuming this is very easy, so I'm hoping you can take a guess. Yeah, exactly. So this capacitance is epsilon A by D. So now as we can see in this particular formula, so we have area, which is the let's say the cross-sectional area of this capacitance, which is, we know that it is fixed. Then the distance between the dielectric is also fixed, and the epsilon is also fixed. So the for a parallel placed capacitor, what do we have? We have a constant capacitance, right? So now just try to understand. So these two devices, if you try to compare now, so this particular contact, let me change the color of the pen, that will help. So this particular contact, let's say I'm talking about this contact as of now, is the gate contact in this device. So let me try to make it again. So let's say this is metal one, which is what I'm talking about. Then this particular contact was a body contact. So let's make that also. Then in between, what do we had in this capacitor to make it constant? It was a constant dielectric, right? So in this also we have two types of devices. So one is we have a constant dielectric, let's say for SiO2. So this is exactly same till now from the parallel plate capacitor, if you can see clearly. But now for a MOS capacitor, we have an additional semiconductor that is placed between these two. So this is what we call a substrate. So now due to this addition of this substrate, what happens is, if I try to make a CV plot of this. So, okay, first of all, can anyone tell me what will be the CV plot of this particular capacitor, which is a parallel plate capacitor? How will it look like in terms of the CV plot? Anyone wants to take a guess? So it is quite clear from this formula how will this capacitor look like. Is it some linear relation, or is it okay? So I've got a comment which is constant. Yeah, so it will be constant with respect to voltage, because once we have fabricated this, or once we have this capacitor in hand, we have fixed the area, we have fixed the diameter, sorry, the thickness or the distance between the two plates, and epsilon is again constant. So it will be remaining constant with respect to the voltage, because ultimately you know that on a large basis, q is nothing but charge into velocity, sorry, it's the opposite. Charge is nothing but capacitance into the voltage. So even if you increase the voltage, what happens? Your charge increases and your capacitance remains constant. So this is how this above figure look like. But now, as I said, due to this addition of this substrate, what happens in an actual MOS capacitor is it starts with the same type of characteristics, and then due to this addition of the substrate, it goes something like this. So it starts to decrease, and then it again increases, and again act like a normal capacitor. So this is how a CV characteristics of a MOS capacitor look like. So we will see how it is actually happening and why it is decreasing and then again increasing. So this is what we'll be understanding in this particular lecture, that why this capacitor is acting like this, not a constant but a variable capacitor. I mean, I think we have established that it will not remain constant because we have added some different things that are not supposed to be in a parallel plate or a constant capacitor. So it will change, but why it is changing like this, we'll be seeing this in this particular lecture. So let's start with the most important thing, which is a band diagram of this particular structure. So we'll be making the energy band diagram. So now, as you can see, we have different interfaces. So one is this gate one is this SiO2, and this is substrate. So for simplicity, I'm taking P-type substrate now because mostly we'll be dealing with the NMOS, and this is again the body. So now we cannot cut it like horizontally, so we need to cut it like this. So to simplify, I'm just rotating this device by 90 degree to make the band diagram. So now, so let's say this is metal, this is SiO2, this is your substrate, and this is your body. So again, I have rotated this device to 90 degree. This is now, so this is, let's say, oxide. This is your P-type substrate, and this is your body. So I'm not very worried about this because nothing is happening here. So the all the interesting things that are happening is actually at this interface of silicon and oxide. So this is what we are majorly interested in, and this is what we are making the band diagram for. I mean, so if I try to extend this diagram, yeah. So let's try to make a band diagram now. Yeah, so for the metal, we already know that the Fermi level is very high of electron. So let's say this is the vacuum line, which I'm denoting as E vacuum. So EFN or the metal Fermi function will be something here. So let's say I'm just assuming. So what is this distance from vacuum to Fermi? I already told this in the last class. So I'm assuming you might be knowing this. The energy required to for an electron to go from Fermi to vacuum is, yeah. So this is work function. So I'm just denoting this as Q phi m, which is a metal work function. And then in between you can see, oh sorry, this is the metal till here. So in between you can see this is the oxide region. So oxide, we know that we have a very large band gap. So let's say this is EV. So EV will be something somewhere here. So this is like very large band gap. It is approximately 8 electron volts in nature. So we are not very worried about this oxide as of now. And the third thing that we had in this is the p-type substrate. So if I try to make a p-type substrate, for example, let me make it here. Let's say this is EV, this is, sorry, EC, this is EV, and then we have EI. So for a p-type substrate, your Fermi level will be close to the valence band, right? So these are the like the band diagrams for three different materials that we have combined. But right now we have not done any uh, analysis on what is actually happening after combining. We have made the separate diagram. So now we can clearly see that we will be having some flow of electrons from higher Fermi to lower Fermi. So which is the case for, so in this what will happen, the electron will flow from metal to the semiconductor because the metal has a higher Fermi level. And in between we know that we have an insulator, but there will be some conduction. So we will see how it is happening and how this insulator is coming into the picture. So let's try to make the actual band diagram now. Sorry. Yeah. So yeah, now what will happen? This band will go down, right? Because what do we have? We have a flow from here to here. So that means If this will go down, then these will shift downwards like this. So let me try to make it. So let's say this is your metal. So since we are not applying any voltage as of now, let me keep this for me as some single line. So this will align as we have already seen. So this is the vacuum. So this will be the metal work function. So now whatever change is happening here, so now the Fermi level is aligned. So to cover that, what will happen? These bands will go down, and this will be your EI. And similarly, in a similar nature, there will be some drop across the oxide also. So I'm just making like the ECAV, which are very far away. So in actual reality, we cannot see that, but yeah, it will be something like this only. So this is the band diagram after we combine these three materials. So this is EF for the metal side, this is EF for the semiconductor side, this is EI, this is EC, this is EV. So now we have already seen in your in the diodes that whatever change happens from conduction band to conduction band, this is nothing but the applied or the built-in voltage. Since we are not applying anything, so this is nothing but the built-in voltage. And let's say the change in your oxide that is happening is Vox. That is a drop across the oxide. So we can clearly see from this diagram that whatever voltage that we are applying is getting changed over your oxide drop and your built-in potential. So this is actually, let's say this is the semiconductor work function, which is what we are applying. So this will be actually equals to your semiconductor work function. If I try to write in very general way, so the drop across the oxide plus the built-in voltage will be your semiconductor work function. And from here only we get the term that we have as the flat band voltage. So as the name suggests, we want to make these bands, which are, maybe I can highlight those. So whenever these bands will be flat, whatever voltage that we have applied at that, sorry, yeah, so whatever voltage that we are applying to make these bands flat will be your flat band voltage, and we will denote it with VFB. So as I've said, we need to keep the bands flat. So in ideal case, the flat band voltage is actually equals to 5 ms. So how it is actually going on, let's see. So let's say this is the gate, this is your oxide. So this is for the ideal case, as I've said. Sorry. Then this is your substrate, and this is your body contact. So now what can happen in reality in whenever we are fabrication certain devices, what can happen is we can have certain trap charges that are being trapped in the oxide layer. So let's say these trap charges are for now positive. So due to these positive charges, there is a voltage drop also. So the actual flat band voltage for practical cases becomes 5 ms minus this trap charges by Cox. So this is actually coming from this Q is equals to Cv only. So the voltage is Q by C. So if let's say if we have some certain trap charges which are also present, we can also have that addition of these in the flat band voltage to make it actually flat. Because these trap charges will either help in your conduction or either destroy your conduction. So let's say we are taking a p-type substrate, for example. So in this, these holes or these positive charges will actually help in your conduction, and that will result in making a flat band condition comes quicker. So that is why we are having a negative sign. So similarly, let's say we had some negative charges, and that will delay your conduction. So this will be overall QSS will be positive because those charges will be negative, and hence we have a smaller flat band voltage for that. So this is the case when we have some non-idealities. But this is very rare. In general, whatever we will be studying in this course will be on the ideal MOSFETs only. So we need to be considering the flat band voltage as the difference between the metal and the semiconductor work function. So now if we see the actual working of this, so will now start to apply certain gate voltage in our MOS capacitor. So now the first case that we'll be taking is we'll be applying a gate voltage which is actually even less than the flat band voltage. So that means we are applying a negative voltage because in a p-type substrate the negative voltage is what we have as a uh, bias. So if I try to make, let's say, the diagram, so let's say this is your insulator, this is your Fermi level which is for the metal EFM, and let's say this is your capacitor, sorry, this is your p-type substrate which is EC EV. So you see here all the diagrams are flat. I mean, sorry, not the diagrams, but the bands are flat. And your EF will be somewhere here, right? So this is what I'm denoting with EFP. So now what I am doing is I want to make this uh, Fermi level align with this. So now what I am doing is I am actually applying a negative gate voltage, right? So and that voltage is what I am applying at the metal. So I have applied a metal negative voltage. So what do you think will happen here? Is your Fermi level going to move upward or downward? We are applying a negative voltage, and your metal is already having a very high amount of electrons. So if I try to have a apply a negative voltage, what do you think will happen to the metal or the Fermi level of the metal? So if you consider it will go down, right? That is true. So if it is going down, then what will happen? So if it is going down, so the flow will be from here to here, right? The band will move upward. Oh, sorry. So no, no, no. So if I am applying a negative voltage, so actually the Fermi level will move closer to the conduction band, right? Because it is already having a lot of electrons. So in actual reality, the Fermi level will move up, or it will go more closer to the conduction band, and overall your band will move up. So it will not go down, it will actually go up because it is going closer to the conduction band. Is this clear? Yeah, so okay. So if you consider example of, let's say, a n-type MOSFET. So let's say we had this, so I'm making this Fermi level. Let's say this is the Fermi level as of now. So even if you give more negative ions to this, so what will happen? This will become more n-type, right? So this Fermi level will tend to move closer to the conduction band. But now in the metal, what you see is, sorry, in the metal, what you see is it is already having a lot of electrons. So your Fermi and conduction are almost overlapping. So the overall idea is it should go up or it should go towards the conduction band or the upward side. Does it make sense? Yeah. So yeah, if the band diagram is going up, okay, so I have a query. No, no. So if it is going up, your work function should decrease, right? Because let's say this is vacuum and this was the Fermi level before and this is now. So this will actually reduce, right? So if I try to, okay, let me try to make the band diagram completely. It will clear your doubts. So what I'm trying to say is your EF will come somewhere here. And again, so the bands are bending like upward. So let me make the insulator like this only. And your bands will move upward like this. And this is your p-type substrate. So Fermi level needs to be aligned. So now you can clearly see here this difference only. So this was phi m and this is phi s, right? So this difference is actually your the applied VFB. So the VFB you can clearly see from this diagram is phi m minus phi s. And now since we are applying a negative voltage, so even if I try to make a MOSFET structure, so let's say this is your oxide, this is a gate, and this is your substrate. So if I'm applying a negative voltage, what do you think will happen at the interface? I'd repeat the question again. So we are applying the negative voltage at the gate, and your substrate, oh, sorry, so your substrate is P type, for example. So once you apply a negative voltage, what do you think will happen to the carriers for the substrate? Yes? Yeah, I'm not talking in terms of Fermi level. Let's say I'm talking about the carriers, actual carriers. So for negative bias, whenever we are applying, so you know the P-type substrate has the majority carriers holes, right? So these holes will actually get attracted towards the semiconductor oxide semiconductor interface, right? So there will be accumulation of lot of holes here, which is actually here in the band diagram. So we will have a lot of holes once we apply any negative bias, right? So that is why this particular region, whenever we are applying the gate voltage less than that of a flat band, that is why we call this region as accumulation region. Because we have accumulation of majority carriers, which are holes in this particular case, near the semiconductor oxide interface. So hence this region is what we call as the accumulation region. So let me write this so that you can also note. So accumulation of majority carriers is happening, which are holes in this case at semiconductor oxide interface. So now what we have established is we have the band bending upwards, and after the flat band voltage there will be some time that comes that the bands will get flat like this, which is this diagram, right? So now the second case that we will consider is whenever the gate voltage goes beyond the flat band voltage, right? So the case 2 that we'll be seeing now is the voltage which is less than, oh sorry, greater than that of flat band. And I'm talking this as, let's say, some positive voltage. Okay, so let me make the diagram again. Okay, I have a query which says why a band diagram is bend to the only, oh, so the band bending is actually happening only at the, okay, as I said, that this bulk part that we see here, there is no change. So whatever the interesting thing that are happening is actually happening at the interface, right? So let's say it has maybe Na, which is 10 is per 17 holes. Once you apply this, all those holes will be getting accumulated at the interface. And this oxide is not letting these holes go towards the metal, right? So whatever change that you see in the field or in anything will be happening at this particular interface. So that is why everything, let's say even the electric field or other plots that will. So if you remember in the last class, we have seen this for PN junction. So whenever we apply certain voltage, there is a depletion region that is formed only at the junction, and the electric field was something like this, if you remember. And here the electric field was zero. We are not considered, or we are not even worried about the bulk, right? So whatever is happening needs to happen at the junction. So hence, whatever the band diagrams that we are making or the change that we are seeing is only at the interface. Does it make sense? Is there any doubt in this? Please let me know if there is any doubt. Okay, great. So we can go ahead. So as I said, now we are applying some positive voltage, so we can make a band diagram. Sorry, not the band diagram, but let's say the schematic again. So now what I have done is I have applied certain positive voltage at the gate. So now again try to understand. We have a P-type substrate, we have oxide here, we have a body voltage here, which is zero. So now once I apply a positive voltage, what do you think will happen at the interface? So you can clearly see here what we have seen, that we have a positive bias, right? So since the majority carriers here are electrons, so I've moved, yeah. So I've seen that we have the majority carriers that are already accumulated when we are applying a negative bias. But now when I am applying a positive bias, those majority carriers will be repelled, right? So the minority carriers that are the Na minus ions, which which are actually the negative ions, will get accumulated or will get come near the surface, and all the majority carriers that are all the free carriers will move away from this. So this is how some region, which is what we are calling as depletion, will come into the picture. So if I try to make a band diagram out of it, so let's say now your Fermi level will move down because of the application of the voltage, and the band will actually move downward. Let's say this is the Fermi level, and now what is happening? Your majority carriers are getting, sorry, your minority carriers are getting here, and this region now, sorry, and this region will now be full of depleted carriers. As we have seen in the PN junction also, this is same to that. So this region will be containing only depletion carriers. So hence your band diagram is going downwards, and because of this depletion of carriers near the interface, we call this region as depletion region. So the first one was accumulation. Now the second one is depletion. Does it make sense? Okay. So now the third thing that we'll be seeing, let's say even if I apply more and more positive bias. So do you agree that these bands will move even more downward? More the positive bias that I will apply, more the bending will be. Agree, right? So even if we are having more bending now, so let's try to have more bend. Sorry. And let's say this was a Fermi level. Sorry, not M. This is the Fermi level for semiconductor. So now what you see here, so if you like look closely at the interface, your Fermi level, which was below the intrinsic level and the in the substrate, has actually went above the intrinsic level at the interface. So let's say this is case 3. So can anyone tell what type of semiconductor it has become at the interface? So it was p-type substrate when we started applying the voltage. Now even after applying more and more voltage, the Fermi level has shifted from below the intrinsic level to above the intrinsic level. So what kind of semiconductor it is? Yeah, exactly. So from a p-type substrate, it has converted to n-type. So it has inverted to n-type. So hence we call this region as the inversion region. So we started from accumulation, right? Then we went towards even more application, went towards the depletion. And after a certain voltage, it happens that we have reached to inversion. So this is the actual practical working of a MOS capacitor. Now we will see why that capacitance actually decreased in that particular CV plot. So before that, let me cover one more important term, which is what we call as surface potential. So in any MOS band diagram, so let me tell you what is surface potential. So let's say this is your Fermi level and this is your EI. This is your EC, this is your EV, this is your EF. So, okay, yeah. So surface potential, which I'm denoting as phi s, is nothing but the difference between the EI at bulk and EI at interface. So basically this, if I try to extend this, and this is what we call as surface potential, which is denoted as phi s. So now if you see here for this particular case, I mean, I'm just trying to give you an example. So we already know that this difference between the Fermi level and the intrinsic is what we call as Fermi potential. And this is EI at the bulk, right? For this particular case. And this is EI at the semiconductor or the interface for this case. So this itself is phi f, right? So for the inversion, what happens is your surface potential becomes twice of the Fermi level. Does it make sense to everyone? Because your surface potential is nothing but the difference between EI at bulk minus EI at interface. So this is your surface potential. Is there any doubt in this? Because this is the most important phenomena that you need to understand. Your semiconductor, which was P type in initial reality, it has converted to N type at the interface. I mean, this is the most beautiful phenomena you will see, that because of this only we are having certain physics that we are studying for this particular course. Is this clear to everyone? Okay, so we can move ahead. So my major point was whenever the surface potential becomes twice of the Fermi potential, that is, whenever the inversion happens, that particular gate voltage is what we call as the threshold voltage. So the definition of threshold voltage is nothing but whenever the majority carrier concentration in the bulk, which was Na, becomes equal to the minority carrier concentration at the interface, right? So whenever the number of holes which was there in the bulk, whenever this N actually becomes Na, is that voltage is what we call as the threshold voltage. Make sense? If there is a doubt, please ask me, because this is quite important to understand. Shall we move ahead? Okay. So what I'm trying to say is, you can see in this diagram, so this difference is nothing but your Na, right? So in a p-type substrate, whenever the majority carriers in the bulk, which was Na, right, becomes equal to the minority carrier at the interface. So in this, whenever the number of electron will become Na here, that means whenever this actual inversion happens here, so this was Na, right? And if you see, this is also the same Fermi potential. So now, but the semiconductor is N-type. So what I'm trying to say is, whenever at the interface, your majority carriers in the bulk, whatever the majority carriers in the bulk are, whenever they become equal to the minority carriers in the interface, that particular voltage is threshold voltage, because that is where the inversion is happening. Is this clear? So the definition of threshold voltage is this only, that whenever your majority carriers in the bulk become equal to the minority carriers in the interface, that particular voltage is threshold voltage. In general, we define it at whenever the MOSFET turns on. That is a very lame, or that is a very vague definition. We need to understand how it is getting turned on. Please let me know if this is clear now to everyone. Okay. So if this is clear, then let me try to now tell you what is the capacitance, or how that capacitance was actually decreasing. So as you clearly know now, that for the case 1, what do we had? We had the accumulation of, after applying a negative bias, so this is the bias, this is the gate, this is the oxide, we had the accumulation of holes, right? So this is what we are calling as case 1, which is accumulation. So it is like acting like a parallel plate capacitor. If you see negative charge, positive charge, and then in between there is oxide. So this is case 1, which is accumulation of majority carriers, and all your capacitance is actually coming from your Cox. So this is constant Cox, right? So let me make Okay, I have got a question. How minority carriers is equal to free charge carrier at interface? Okay, so let me quickly try to explain this and then I'll answer your question. So this is a good question. Let me complete this first. So as I said that in the case one, we had the negative charges or the negative application of the voltage, and your holes got attracted towards your surface. So this is like a parallel plate capacitor. One side we have a negative, one side we have positive, and in between we have oxide. So your capacitance will be constant. So let's make that here. So till your flat band voltage, your capacitance is actually constant, right? So now your case two was depletion. So we have applied some positive bias. So from applying that positive bias, what was happening? We were having an additional region which only contains the acceptor ions. Sorry. So let's say this was gate and some positive voltage was applied. Let me make positive ions here. So now you see, what do we have? We have one C oxide which was there before, and we have additional capacitance which is C depletion, right? Because this is a depletion region and this has some different dielectric. So can we write this is a series combination of C ox and C depletion, which is in reality the formula we apply is this C depletion upon C ox plus C depletion. So whenever we have two series capacitance, you know your overall capacitance would decrease, right? Any doubts in this? How this curve decreased? I mean, are you able to understand now that how wide this curve has actually decreased? Okay. So now actually in the third case, what happened was there was a complete inversion, right? So let's say we applied some positive gate bias here. So we applied so much that your interface actually had those electrons. That depletion remained there. That is not a problem. But your capacitance is only now this inverted capacitance, which is this. Because you already have a plate here that is made up of the minority carriers, which are electrons in the case. So this, when once you reach the inversion, your so this is inversion, your capacitance will go again to the constant Cox. So that inversion happens whenever you have a threshold voltage. So let's say this is a VTH. So your capacitance will decrease or increase again, and it will again come something like this. So now the curve is clear. How this curve is actually made. Please let me know if there are any doubts. But this is quite important to understand. So hence I'm repeating again and again. Okay. So as I said, let me repeat again. So as I said, whenever I'm applying a negative bias, we had the accumulation of holes. So this is like a capacitor which has negative on one side, which has positive on other side, and in between we have a dielectric. So this is like a parallel plate capacitor with having a constant value of Cox, which is this region, right? Now in the second, whenever we applied a positive bias, so what happened? We created an additional depletion region here, right? So this is now this was before also this Cox, but now there is one more dielectric. So this is a series combination of Cox and C depletion, due to which your capacitance decreased, which is actually this. Sorry, which is actually this. Is this clear till here? Yeah. So once you apply so much gate bias that your actual electrons which are here becomes equals to your minority carrier. So this is now itself is a capacitance, right? This is a positive bias and this is a very thin layer of your minority carriers, which are now equal to your concentration of majority carriers. So basically what I'm trying to say here is here N has become equals to Na. So whenever this happens, your oxide capacitance is exactly the same and it has come again to your Cox, which is actually this. Does it make sense? Any doubts? Okay, fine. So what I'm trying to say is, okay, let me make the diagram again. So I applied positive bias. I had an oxide, and you know that we had a depletion region, that is true. But now what I'm trying to say here is, because we know that the inversion has happened, I specifically told at this diagram that here your N has actually become Na, right? So your electron, we have a sheet of electron here, right? Like the holes that were accumulated. So let's say we have a sheet of electron here. So this is a positive metal gate. No, I'll repeat again. So this is a positive metal gate, this is a negative metal gate, and this is our oxide. So it has also become oxide capacitor, right? Like the case it was in accumulation. It has completely inverted. In accumulation, we have negative bias but positive holes. Now we have positive bias but negative electrons. This is the only difference. Does it make sense? So this is your Cox. Is it still confusing? Okay. So hence your oxide capacitance increased here. So the depletion region has not gone away. It's still there. So we have some depletion width into the picture. But your sheet of electron has made it a constant capacitor, because in this case N has become Na. So I think this also answers the previous question that has been asked, that how minority carrier is equal to free charge carrier at the interface. Is this clear, everyone? Okay, great. So now what we have seen is we started with the application of negative bias, then we reached flat band in some in between. So this was the negative bias, then we reached flat band in between. So and then we reached depletion, and then ultimately we reached the inversion, right? So now if I try to break it up, so we can actually calculate the threshold voltage from this, so which I'm denoting as VTH. So step one is we need to actually achieve the flat band, right? So your gate voltage till now will be equal to the flat band voltage, and for flat band we know it is 5 ms only. So step two, you need to deplete the carriers, right? To reach the VT, you need to deplete the carriers at oxide semiconductor interface. And for that, we require a certain gate voltage that is flat band plus, let's say we have some depletion charge over Cox. This will still remain the same. Is this clear till here? So the step three, what will be the step three? Can anyone tell? Yeah, up to inversion, right? Yeah. So your gate voltage will be now flat band, now the depletion, sorry, plus the inversion, which is the surface potential, which will be 2 phi f for the case when we are reaching the VT. So your threshold voltage actually becomes this. So this is the threshold voltage that we are talking about. It is VFB plus Q depletion over Cox plus 2 phi f. And your depletion width that I'm talking about actually comes from the Poisson equation only. So if you remember in the last class, we derived this Fermi potential, or the potential which is Qna by epsilon s x square by 2 minus xt dot x plus Qna by 2 epsilon s xt square. I mean, you can check the last class also. This is already derived. This comes from the Poisson equation. So now we need to see that your surface potential, sorry, your surface potential is nothing but the potential at s equals to 0, right? Which is at the interface. So if I put x equals to 0 here, your surface potential is equals to, so this will be 0, this will be 0, only this term will be there, right? So it will be q n a x d square over 2 phi s. And from this, the xd will come out to be under root 2 epsilon s phi s over q n a. And your phi s is actually 2 phi f. So this is your depletion width. Please let me know if you have any doubt in this. Is this clear? Yeah. So we have the depletion width, and we can also calculate the depletion charge, which is again nothing but q and xd. So xd when put here, it will come out to be under root, it should come out to be under root 2 q n a epsilon s phi s. And again phi s will be 2 phi f if you are talking about the maximum depletion width. So your actual threshold voltage will become now VFB plus Q depletion, which is this we have just calculated, upon Cox plus 2 phi f, or psi s, you will write, and this psi s is actually 2 phi f. Please let me know if you have any difficulty in understanding this threshold voltage, because this is the most important formula, and this will surely, I think, come in your exams also. Are you able to understand that we went from flat band to the depletion to the inversion, and at that particular inversion point, when your psi s become 2 phi f, we have written, or we have reached to the threshold voltage. Is this clear to everyone? Please, yeah. Oh, okay. This thing you're talking about? Oh, this is the overall charge, right? I mean, we know that, if you remember, the overall charge density, the row that we plotted, this was for a PN junction, it was something like this, right? ND, So the area of this is nothing but the overall charge, right? So this is, I'll just write QNA, which is the y-axis, and the depletion width is, let's say, XD. So this is what I've just written. I mean, this is a PN junction, so for this case, this is only this. Is it clear? Okay. And then if you put this XD here, that is QNA multiplied by this, so this QNA under root will come up, which has come up. Sorry. Hmm. Is this clear to everyone? Okay, so let's move quickly to the questions now. We have covered a lot of concepts, so I would say please revise this lecture. I'll upload the video on YouTube. Please go through it again, because these are the very important concepts. So let's go towards some of the problems now, which are, I think, relatively easy for you to know, for now you to answer. So this is the first problem. What is the answer? Please quickly write in the chat box. So MOSFET is a, yeah, so it is a voltage control device. We have already seen that BJT is a current control device and MOSFET is a voltage control device. Okay, so let's do a numerical now quickly. So I would suggest everyone quickly open your notebooks and pen, and you try to have the answers ready with you. So we have a MOS capacitor that we have just studied, which is having Na. Na means it is what type of a MOS capacitor? Is it a NMOS or a PMOS? Yeah, it is a P-type substrate, that is true, but a P-type substrate is actually a NMOS, right? And an N-type substrate is actually a PMOS. So it is a N MOS cap. Whenever we have p-type doping, will have a N MOS. So Ni is already given. You need to calculate the Fermi potential. Will you be able to do it? What is the formula? Can anyone tell to solve this? What is the Fermi potential? Or what is EF minus EI? We have done this like 100 times now. Anyone? No answer still. So if you remember this formula, what was this formula? N equals to Ni. Then, yeah, EF minus EI over KT, right? So from this, if you remember, we calculated EF minus EI will be nothing but KT by Q, that is, let's say VT ln Na over Ni. I mean, for this case, it will be Nd, right? So this is your Fermi potential. This is VT ln Na over Ni. So you have everything given in the question. Quickly let me know what is the answer. Is this clear to everyone how this Fermi potential is getting calculated? Please quickly say yes or no, everyone. Is this clear? Please let me know if it is clear. So if you remember, this is EI, this is EF for a p-type substrate, and this is your Fermi, right? So we can write P is equals to Ni exponential EI minus EF over KT. And from this you can calculate the Fermi potential, which is VT ln Na over Ni. So I've already got some answer, which is option A. So let's see. So it will be Fermi potential will be 0.026 times ln Na, which is 17, and okay, so this will be times for 7 basically, which is 0.026 times 7 times 2.303. So 14 times 2 will come out to be 10 times 3 will come out to be 218, 3. So yeah, it's something 0.4. That is correct. So option A is the correct answer. Is this clear to everyone? Shall we move ahead? Okay. So let me do some important questions first. Okay, so this is one question. So let's say it is saying that we have a MOS capacitor with Na is equals to this, Ni is equals to this, with oxide thickness is also given. Your Ks is also given. That means your epsilon permittivity. We need to compute the depletion layer thickness and electric field at the surface on the onset of strong inversion. So can you tell what is the formula for your depletion width at the onset of inversion? I just told you, I think, if you remember. Anyone? And psi s. And at the onset it is 2 phi f. So phi f you can again calculate using VT ln Na over Ni, right? And then epsilon s, it's nothing but 11.8 times epsilon naught, which is 8.85 times per minus 14 in centimeter. Na is given in the question, and Q you already know. So quickly let me know the answer. Maybe you can take 2-3 minutes and let me know the answer quickly. Did anyone got any answer? Okay, so I've done some calculations. I'm getting 3537 centimeter, which is 35.37 7, which is 35.37 nanometer, which is option B. So electric field you can also calculate. Max is again at the interface. So it's again just it will be 2q5 SNA. So it is nothing but V by L. I hope you already know this. So you can get it. So you will, I think, get the next option, which is 5.4 to 10 volt per centimeter. Are you able to calculate your depletion width? I hope you also got the same answer. I did some calculation, got get this. Okay, let's move ahead then. Okay, so it says the next problem says a high frequency mass capacitance versus voltage characteristic. So if you okay, just consider this as of now, high frequency we'll study in the next lecture because it might confuse you. Is sketched below. We need to assume that the semiconductor is silicon. Is at room temperature the semiconductor is what? Is it P type? Is it N type? Is it intrinsic? Is it PN junction? Quickly let me know what is the answer. It is asking that semiconductor is what type. You need to be very clear. Semiconductor is what type. It is not asking what is the type of a MOS cap. It is asking the type of semiconductor. Yeah, it is a P type semiconductor because it is a NMOS cap. You can clearly see the flat band is coming here and then your threshold is coming here. So it is a P type semiconductor. So option B is the correct answer. Okay, let's see some more questions if I have. Let's skip these for now. Yeah. Okay, so it's the same question. Okay, so this is the same question. I think there's 35 point something that was nanometer. So yeah, I'll not repeat this. Just wait. Yeah, this is one more question that we have. So it again says a high frequency MOS capacitance versus voltage is given. We need to find the thickness of oxide. Can you even tell what formula will you use to calculate this thickness of oxide? No, depletion width is inside the semiconductor. Now I'm asking you to calculate the thickness of oxide. So so this is your oxide, this is your depletion width. We are not applying any bias, so it is asking you to calculate this Tox. What will be the formula for this? What is this? Cox into epsilon ox. Okay, so Cox will be nothing but epsilon ox over Tox. So your Tox will be epsilon ox over Cox. And what is the value of Cox? So this is per unit area, obviously. So Cox you can clearly see from the diagram, right? What is the value of Cox from this diagram? Can anyone tell? It's clearly visible, I mean. Yeah, it's 1.15 multiplied by 10 square minus 6 farad per centimeter square. So you now need to calculate Tox from that. So its epsilon ox is nothing but 3.9 times 11, sorry, not 11, 8.85 into 10 is for minus 14 divided by your COx, which is 1.15 to 10 is for minus 6. So this answer will come in centimeter. So if you quickly calculate it, it would be good. Please let me know what is the answer that you all are getting. Okay. So option B is the correct answer. It will come out to be 3 nanometer. Is this question clear? Are you all able to understand how a MOS capacitor works and how the transition is happening from accumulation to depletion to inversion? Then what is actual physics? How are the carriers moving and how it is mathematically reducing? Is there any doubt in that? Because it is the most important concept. I mean, uh, in any interview, if you face it, the people will ask you these questions only, even for any research interview or any industry interview. If there is any doubt, please let me know. Otherwise, we can move ahead. Okay, so I'm assuming it is clear. So let's try to have one or two more problems, which are very generic in nature, which is a MOSFET problem actually. So I didn't want to cover that in this particular lecture, but yeah, these are all very generic. So I think we can cover these two problems actually. So we have a MOSFET here, which is having a gate to source voltage. So source is gate and source. I mean, I'll let you know what is the source and drain. But in general, I mean, you already, I hope you are already aware that we have two different regions that are there present in a MOSFET, which is saturation and linear region. So we have already seen as of now for MOSFET, whenever more VGS equals to VT, it gets turns on, right? So in this also we have two categories. We have when VDS is less than VGS minus VT, and when VDS is greater than VGS minus VT. So this region is what we call as linear, and this region is what we call as saturation. So for linear region, your IDS comes out to be mu and Cox W by L VGS minus VTH times VDS minus VD square by 2. So this is for linear. And for saturation, it comes out to be 1 by 2 mu and Cox W by L VGS minus VTH whole square. This was saturation. Are you all already aware of these formulas? Can you tell? Okay, if they are already there, okay, that is great. So in this MOSFET, it is given that the drain to source voltage, your VDS is actually threshold voltage plus 2 volts, and then the drain current, it is asking your drain current if Kn is equals to this, and in this MOSFET you can clearly see your gate and drain are actually grounded. So what kind of MOSFET is it? Is it in linear region or is it in saturation? Anyone? If your gate voltage is equals to drain, what do you think? Is it in saturation or linear? Okay, let me try to explain it. So it is saying basically your VDS is actually equals to your VGS, right? Because this is grounded to this. So if this term is actually equals to this, Which relation will hold from these two? So for saturation, as you said, your VDS needs to be greater than that of VGS minus VT, right? So if these two are equal, so it has to be true because these two are equal. Then addition of this will be lesser, right? So it is in saturation. Is it clear to everyone also that how is it in saturation? So now we can use this formula because it is in saturation. So IDS is equal to, so Kn is already given as mu and CFW by L. So it will be 1 by 2 Kn. VGS minus VT is actually because VD is equals to VG equals to this. So it is VTH plus 2 minus VTH whole square. So this will come out to be 4 Kn by 2 means Q 2 Kn, which is option A. Is there any doubt in this? Okay. So I hope we are able to understand. I mean, all of us are able to understand now how actually a MOS capacitor works. So you can see clearly that we are only able to cover this band diagram and CV characteristics in this particular topic. And then we have seen some of the calculation of threshold voltage. So we are still left with the MOSFET IV and the channel approximation on all these things in a MOSFET. So we'll be starting with these topics in the subsequent lecture because this is again very important and some part of the transport theory also. So if you don't have any doubts in the MOS capacitor, we can actually wrap up the session. So quickly let me know if anyone has any doubts. Otherwise, we can wrap up the session for today. I am again telling this is the very important concept you need to understand because I mean you need otherwise you won't be able to like easily clear your exams and all those things. Quickly let me know if everything is clear or if you have any doubts for today's whatever we have learned today. Otherwise, we can wrap up the session. What is this? Please answer my question. What is your question? Are you talking about this how minority carriers is equal to free charge carrier concentration as interface? So this I have already explained again using this diagram if you remember. So as I said in this diagram that these electrons are actually now the sheet of electron and here it actually N is becoming Na. So this is a constant capacitance. So your question is how minority carriers is equal to free charge carrier. What do you mean free? So your N is actually becoming Na, right? Your It was a P-type substrate. So in this we know that your P was Nd. Oh sorry, Na. And here the inversion has happened. So actually those carriers has now become N. So this is what I was talking about when I was saying inversion. So your band diagram, if you see, for me, if this was phi f, now this was also phi f, and this is what we called as the surface potential. So your this Fermi has actually become this Fermi, which is now your N type. Your N has become N, right? Is this clear? Or is it clear? How? Is it still not clear? Okay, yeah, great. So I think we can wrap up the session. So is there anyone who has any questions? Let me stop the recording.